Year 13, Chapter 5, Differentiation, Lesson 1, Points of Inflection and Concavity. So in this lesson, we're going to explore the concept of stationary points of inflection. We will start by investigating a function and finding out what we can about the different features of this function. So here is the function, y equals x cubed minus 3x squared plus 3x minus 2. So I'm going to start off by differentiating this function, which means we need to write down dy by dx. So dy by dx, 3x squared minus 6x plus 3. Very simple function. So let's now consider any stationary points. Now we know at any stationary points, dy by dx is equal to 0. So we are going to set dy by dx equal to 0 and then solve the resulting equation. So we have 3x squared minus 6x plus 3 equals 0. Let's divide all three terms by 3. So this gives me x squared minus 2x plus 1 equals 0. And this then factorises very easily to give me x minus 1 squared equals 0. So I get x equals 1. So there must be a stationary point at the point x equals 1. Now let's see what else we know. Let's calculate the value of y by substituting back into the original function here. So we can find out that when x equals 1, y is equal to negative 1. Now, let's find the second derivative, d2y by dx squared. So to find the second derivative, we need to take the first derivative up here and we need to differentiate it again. So d2y by dx squared is equal to 6x minus 6. And what I would like to know is, at this point x equals 1, which we've just established, is some form of stationary point, what is d2y by dx squared equal to? So if we substitute x equals 1 into d2y by dx squared, we get an answer of 0. Now we know if the second derivative is positive at a stationary point, then we have a minimum point. We know if the second derivative is negative at a stationary point, then we have a maximum point. But what happens if the second derivative is equal to 0? So this is clearly not a maximum or a minimum point. And we need to do some further investigation of it. So the result that we found doesn't fit into either of the first two categories of a minimum point or a maximum point. So we need to find out, what does it mean that the second derivative is equal to 0 at this point? So we're going to check the value of dy by dx, the first derivative, at either side of this point where x equals 1. So I always like to set my working out neatly and clearly in a table when we're checking the sign of dy by dx at either side of a stationary point. So we'll fill in the values in this table. So we know when x is equal to 1, then dy by dx is equal to 0. We've identified that this is where there's a stationary point. So what happens if x equals 0.5 and what happens if x equals 1.5? Let's substitute into the first derivative, and remember we've worked it out previously, dy by dx is equal to 3x squared minus 6x plus 3. And we find out that dy by dx is 0.75, so positive, when x is equal to 0.5. And when x is equal to 1.5, dy by dx is again 0.75, so still positive. So this does not fit into the pattern that we would expect for a minimum point, where we would expect a negative gradient, a 0 gradient, and then a positive gradient. And it doesn't fit into the pattern for a maximum point either, where we'd have a positive gradient, a 0 gradient at the stationary point, and then a negative gradient. We have something that looks like this. We have, first of all, a positive gradient, then we have a 0 gradient at the stationary point, and then we have a positive gradient again. So x equals 1 for this curve is not a minimum point, it's not a maximum point, it is what we call a stationary point of inflection. So x equals 1, dy by dx is 0, d2y by dx squared is also equal to 0, and we have what is called a stationary point of inflection. Let's have a look at the shape of the curve. So here's a sketch of y equals x cubed minus 3x squared plus 3x minus 2, and hopefully the first thing that you can notice here is this stationary point, and you can see the gradient essentially become 0 at this point. So here is our stationary point of inflection. Now, if you look at the gradient of the curve either side of this stationary point of inflection, then you can see very clearly that here the gradient is positive, and after the stationary point, the gradient is still positive. And this is why we don't have a maximum or a minimum, and we call this a stationary point of inflection. Now, we could have had the situation where we had a negative gradient, and then a 0 gradient, and then a negative gradient. So stationary points of inflection can be mirror images of the one that we can see in this particular curve. So let's summarise everything we know so far. We know that if dy by dx is equal to 0 for a curve, this tells us that we have a stationary point. Now, from here, we know that there are 3 possible outcomes for a stationary point. Now, what are the 3 possible outcomes? We could have a maximum point, we could have a minimum point, or we could have a stationary point of inflection. What else do we know about each of these 3 possible features? Well, we know that at a maximum point, the second derivative, d2y by dx squared, is less than 0. At a minimum point, we know d2y by dx squared is greater than 0. And at a stationary point of inflection, we know that d2y by dx squared is equal to 0. We can also use our knowledge of dy by dx at either side of a stationary point to identify which type of stationary point it is. So, for example, for a maximum point, we know the gradient is 0 at the maximum point. Before the maximum point, the gradient must be positive. After the maximum point, the gradient must be negative. This is reversed for a minimum point. At the minimum point itself, the gradient is 0, but before the minimum point, the gradient is negative. After the minimum point, the gradient is positive. Now, for a stationary point of inflection, the gradient is of course 0, but before the stationary point of inflection and after the stationary point of inflection, the gradient will be positive in both cases, or it could be the other way around, and we have a negative gradient, then a 0 gradient, and then a negative gradient again. And it's important that you learn to identify different types of stationary point using these criteria. And in particular, these criteria here are very important because they will always give you the correct identification, as you will see later on. So we're going to have a look at a worked example together. We need to find and identify all stationary points of the function y equals 3x to the power 5 minus 5x cubed plus 1, and then we will sketch the curve. So remember, we are hunting for stationary points. So we know at stationary points dy by dx is equal to 0. So our first job is to find dy by dx, which is very simple, 15x to the power 4 minus 15x squared. So we can take this first derivative, and we can set it equal to 0. And we can divide through by 15. So we have x4 minus x squared equals 0, x to the power 4 minus x squared equals 0. And then do not divide through by x squared, which would result in us losing an answer, a root. We need to factorise x squared, so we have x squared bracket x squared minus 1 equals 0. This then gives us three possibilities. We either have x equals 0, or from here we have x equals 1, or x equals negative 1. So we have three stationary points, and what we can do is we can substitute back into the original function up here to calculate the matching y-coordinate of each stationary point. So when x is equal to 0, y is equal to 1. When x is equal to 1, y is equal to negative 1. And when x is equal to negative 1, y is equal to 3. So we have three stationary points to investigate. So the next thing that we're going to do is investigate the second derivative, d2y by dx squared, which is equal to 60x cubed minus 30x. Make sure you differentiate the first derivative carefully. And what we're going to do is now investigate the value of d2y by dx squared at the different stationary points. So x equals 0, x equals 1, and x equals negative 1. Let's evaluate the second derivative. So at x equals 0, I find that the second derivative is equal to 0, which means I will investigate this further. It's likely to be a stationary point of inflection, but we will do some further investigation to confirm this. At x equals 1, d2y by dx squared is equal to 30, which is of course greater than 0 or positive, which implies that we have a minimum point. At x equals negative 1, the second derivative is equal to negative 30, which is less than 0, which of course tells us that we have a maximum point. So now let's investigate further the point at which x is equal to 0. And what I'd like to do is set up a table to evaluate dy by dx at different values of x. So negative 0.5 is just before the stationary point. 0 is where the stationary point is, and we know that dy by dx is equal to 0 at this point. And 0.5 is just after the stationary point. And what we're going to do is we're going to substitute negative 0.5 and 0.5 back into the value of dy by dx. And just to remind ourselves, we know that dy by dx is equal to 15x to the power 4 minus 15x squared. And what did we discover? Well, at x equals negative 0.5, the first derivative is negative 2.8125, which of course is less than 0 or negative. At x equals 0.5, the first derivative is also negative 2.8125, so still negative, which means that we have the situation where we have a negative gradient, then we have a 0 gradient, then we have a negative gradient. So this is indeed a stationary point of inflection. And using the first derivative allows us to confirm this. Now you may be wondering why I didn't just confirm it after I knew that the first derivative was equal to 0, but as you'll find out later on, that may not always be enough to confirm what you are looking for. Now let's have a look at how we can sketch the graph from here. So let's mark on what we know so far. At x equals negative 1 and y equals 3, we have a maximum point. This sketch is not to scale. And at x equals 1, y equals negative 1, we have a minimum point, and then at x equals 0, we have a stationary point of inflection. So I'm going to aim to sketch a curve through this. So here's a quick sketch of the curve, and then here is a computer-generated sketch as well. So remember, this is y equals 3x to the 5 minus 5x cubed plus 1. And there's our stationary point. You can see it really clearly on the computer sketch here, where the gradient just becomes 0 at that point of inflection. You can also see nice and clearly the maximum point and the minimum point. So we're now going to explore stationary points in a little bit more detail, and we will identify what we mean by concave and convex curves. So let's think about the second derivative. If the second derivative, d2y by dx squared, is greater than 0, so positive, then this tells us that this portion of the curve is what we call concave upwards. If the second derivative is less than 0 for a portion of a curve, then this part of the curve is said to be concave downwards. Now, it's really important that we know this terminology. There are other terms used here. Concave upwards is also sometimes called convex downwards, and almost the exact opposite of that, concave downwards is called convex upwards. But the terms that you will see used are concave upwards and concave downwards. So we'll focus on this terminology. Now, really, to understand more about what these terms mean, we need to look at an example involving a graph, and that's what we're going to do next. So the example that we are going to investigate is y equals x cubed minus 6x squared plus 6x plus 2. So my first task is to differentiate this. dy by dx is equal to 3x squared minus 12x plus 6. And so that I've got this information ready for use later, I'm also going to differentiate again to find the second derivative, d2y by dx squared, which is 6x minus 12. So the first thing that we will do is we will use the first derivative to identify any stationary points. So this means that we need to set 3x squared minus 12x plus 6 equal to 0. Let's divide through by 3, so x squared minus 4x plus 2 equals 0. And this isn't going to factorise, but it does have roots. So if I complete the square, x minus 2 all squared minus 2 equals 0. So I will get x equals 2 plus or minus root 2. So I have stationary points at x equals 2 plus root 2 and x equals 2 minus root 2. So we're now going to use the second derivative to classify these stationary points. I'll substitute each of these into the second derivative and find out what type of stationary points we have, if we can. So what do we find out? At x equals 2 plus root 2, the second derivative is positive, which means that this gives us a minimum point. And at x equals 2 minus root 2, the second derivative is negative, which means that we have here a maximum point. So we're now going to explore d2y by dx squared a little bit further. Now, something that some of you may have noticed is if we set the second derivative equal to 0, this results in a very simple equation, 6x minus 12 equals 0, which gives us x equals 2. But we know that the first derivative is not 0 at this point, because when we solved the equation where the first derivative was equal to 0, when dy by dx was set equal to 0, there were only two roots, 2 plus or minus root 2. So 2 is not a point at which dy by dx is equal to 0, and we can actually check this further. So at x equals 2, I can evaluate dy by dx and see what it comes to. So x equals 2 dy by dx is equal to -6, which is not equal to 0. So what we know is that x equals 2 is not a stationary point of inflection. So what do we have at x equals 2? We have a non-stationary point of inflection. So to analyse that in a little bit more detail, the fact that it's a non-stationary point of inflection, the non-stationary part, tells us that dy by dx is not equal to 0, and the point of inflection part comes from the fact that d2y, the second derivative, d2y by dx squared, is equal to 0. Let's have a look at what this curve actually looks like. So here is a computer-generated sketch diagram. Let's identify some of the key points here. So we know this point here, which is very clearly a maximum point. That's the point at which x is equal to 2 minus root 2. And this point here, very clearly, is a minimum point. And this is the point at which x was equal to 2 plus root 2. So there's our maximum and minimum point. Now, our non-stationary point of inflection occurred when x was equal to 2. So that's this point here. Now you can't see anything on the curve itself, and that's because it's not a stationary point. So you're not going to see the gradient flatline at all. So let's just mark that on. That is our non-stationary point of inflection. And let's take a further look at this second derivative. So let's remind ourselves d2y by dx squared is equal to 6x minus 12. So we know at x equals 2, this second derivative is equal to 0. But what happens if we explore? What happens when the second derivative is greater than 0? Well, this would give us a very simple linear inequality. 6x minus 12 is greater than 0, and x is greater than 2. But we looked at this a little while ago, didn't we? When the second derivative is greater than 0, we know that that portion of the curve is described as being concave upwards. And I'm going to highlight this on the graph. So see where I'm highlighting orange? This is where the curve is concave upwards. Now, what if we investigate where d2y by dx squared is less than 0? Well, this gives me 6x minus 12 is less than 0, and x is less than 2. So on the other side of my non-stationary point of inflection. And what do we know about the second derivative being less than 0? At portions of the curve where this is true, we say the curve is concave downwards. And I'm going to highlight this in purple. So where x is less than 2, in purple you can see that, this is where the curve is concave downwards. And we need to remember that these terms, concave upwards and concave downwards, relate to the second derivative and whether or not it is positive or negative. So let's summarise these findings so far. We know that at a point of inflection, the following must be true. d2y by dx squared, the second derivative must be equal to 0. Now, if dy by dx equals 0 at this particular point, we then know we have a stationary point of inflection. If, however, dy by dx is not equal to 0 at this point, then we have a non-stationary point of inflection. So let's now summarise the difference between curve sections which are concave upwards and which are concave downwards. So if part of a curve is concave upwards, then we know that d2y by dx squared is greater than 0 for that section of curve. If a curve has a section which is concave downwards, then we know that d2y by dx squared is less than 0. And the curves will have very distinct shapes. If a curve is concave upwards, then it will have a shape like this or like this. And if you join up 2 points on the curve to create a chord, the curve falls underneath the line if it is concave upwards. Now, the opposite is true. If we sketch a curve that is concave downwards, it will look like this or like this. And if we join up 2 points on the curve with a chord, you can see that the curve falls or lies above the line. So this is a good way of distinguishing which sections of your curve are concave upwards and concave downwards visually. You can then clarify this by using the second derivative. Now this leads us to a definition of a point of inflection. We can say this is a point at which a curve transitions from concave downwards to concave upwards or vice versa. Make sure you understand this definition. It will be important later on when we look at certain cases where some interesting things happen. So let's have a look at another worked example together. We're going to consider the function y equals x cubed minus 6x squared plus 15x minus 10. And for part 1, we're going to show that there are no turning points. Now, let's just remind ourselves of what a turning point is. We know that a turning point is a maximum or minimum point. So that's quite interesting because turning points does not include points of inflection. It's simply maxima or minima. So we need to make sure we differentiate first of all, find dy by dx, which is equal to 3x squared minus 12x plus 15. And let's set this equal to 0. And we now have a simple quadratic equation. Divide by 3, x squared minus 4x plus 5 equals 0. And I'm now going to explore the discriminant of this quadratic equation. A equals 1, b equals negative 4, and c equals 5. So remember the discriminant, b squared minus 4ac, would then be equal to negative 4 squared minus 4 times 1 times 5, which gives me negative 4, which is clearly less than 0. So the fact that the discriminant is negative tells me that x squared minus 4x plus 5 equals 0 has no real roots. So what does this tell me? This tells me there are no values for which dy by dx equals 0, which of course tells me there are no stationary points at all of any kind. So no turning points, because a turning point is a type of stationary point. So now, part 2, we've got to find any points of inflection. We won't find any stationary points of inflection, but if we explore d2y by dx squared, we might find a non-stationary point of inflection. The second derivative is equal to 6x minus 12, and if we set the second derivative equal to 0, this then gives us 6x minus 12 equals 0, so x is equal to 2. Now, if we set d2y by dx squared greater than 0, this leads me to 6x minus 12 greater than 0, which gives me x is greater than 2. If I set d2y by dx squared less than 0, this leads me to 6x minus 12 is less than 0, or x is less than 2. So the second derivative changes from negative to positive either side of the point x equals 2. So x equals 2 is a non-stationary point of inflection. We know that this curve has no stationary points, so x equals 2 is not a stationary point, but it is a point at which the second derivative is equal to 0. And it's a point at which the second derivative changes its sign from positive to negative, or negative to positive going left to right. So the curve switches from being concave downwards to being concave upwards. So the last part of this question involves us finding any roots of x cubed minus 6x squared plus 15x minus 10 equals 0, i.e. points at which the graph crosses the x-axis. So there are various different ways in which we can approach this question. I'm going to look at using the factor theorem, and I'm going to test out some values. So I'm going to test out x equals 1. So if I substitute x equals 1 into this, I get 1 cubed minus 6 times 1 squared plus 15 multiplied by 1 minus 10, which gives me an answer of 0. So this implies that x equals 1 is a root. Now, this tells me that x minus 1 is a factor of the original polynomial. And what I can do is I can take x cubed minus 6x squared plus 15x minus 10, and I can divide it by x minus 1 in an attempt to factorise it. So I'm going to do the polynomial division. You may want to pause here and try it yourself, or follow the video along. So I will get x squared here. Multiplying back gives me x cubed minus x squared. Subtracting then gives me minus 5x squared plus 15x minus 10. So I get up at the top minus 5x, multiplying back, minus 5x squared plus 5x. Subtracting then gives me 10x minus 10. So up at the top, very simply, I have a plus 10, and of course multiplying back then gives us a remainder of 0. So what we can now do is write the original function as a product of the linear factor and the quadratic factor. So remember, the equation that we were solving here, we can now write in its factorised form, x minus 1 multiplied by x squared minus 5x plus 10 equals 0. We've dealt with x minus 1, and we know that x equals 1 is a root, but what happens if we set x squared minus 5x plus 10 equal to 0 and try and solve this? Well, I'm going to do what we did previously, and I'm going to explore the discriminant. So remember, this is b squared minus 4ac. So b is equal to negative 5, so that's negative 5 squared, minus 4 multiplied by a, which is 1, multiplied by c, which is 10. So this then gives me a value of negative 15. So my discriminant is less than 0, which implies that the quadratic factor has no real roots. So the only overall root for the original equation up here is at x equals 1. So here is a sketch of the curve. Now let's identify the key features. So we know x equals 1 is where we have a root, and we know that this point here is our non-stationary point of inflection, which occurs when x is equal to 2. Now we know that when x is greater than 2, this is where we have the curve defined as concave upwards. So we know that d2y by dx squared is greater than 0. We also know that in this portion, the curve is concave downwards. And d2y by dx squared is less than 0. And of course, demarking this is in the middle is the non-stationary point of inflection at x equals 2, where d2y by dx squared is equal to 0. Now let's see if those other tricks that we talked about actually apply. I'm going to pick 2 points in the orange section, join them up. Can you see that the curve falls underneath the line, concave upwards? In the purple region, pick 2 points and join them together using a chord. You can see that the curve lies above the line, and we have a portion of the curve that is concave downwards. Now, at this point, I'm going to issue a warning because there are certain cases where things are not necessarily what they seem, and it's worth us doing a little bit more exploration before we generalise too quickly. So I want us to consider the function y equals x to the power 4 plus 2. First thing we're going to do is we're going to identify dy by dx. Very simple piece of differentiation. Dy by dx is equal to 4x cubed. Now, if the first derivative is equal to 0, well, this only gives us x equals 0. What about the second derivative? Does that tell us anything? d2y by dx squared is equal to 12x squared. And at x equals 0, the second derivative is then equal to 0. And there are no other solutions to the equation d2y by dx squared equals 0. So far, this would imply that we have a stationary point of inflection. But this is not exactly what it seems to be. And we're going to sketch the curve to see what really happens at x equals 0. So here is a sketch of y equals x to the 4 plus 2. And I want you to look at the point where x is equal to 0, because this is not a stationary point of inflection. It is not any kind of point of inflection. This is a minimum point, and it's very apparent from the graph that this is a minimum point. So it is not a stationary point of inflection. Now, how could we confirm that this is very definitely a minimum point rather than any kind of point of inflection? Well, the answer lies with the first derivative, and that's exactly what we're going to go back and look at. So let's take the x value of 0 and let's explore what happens either side. So x equals negative 0.5 and x equals 0.5. Now at x equals 0, we know that the first derivative is 0 and we know that the second derivative is also 0. But what happens at x equals negative 0.5 if we substitute into the derivative, the first derivative? Well, we find that at negative 0.5, dy by dx is negative 0.5, so a negative value. At x equals 0.5, the first derivative is positive 0.5, so a positive value. So what does this tell us? This tells us that the gradient goes from negative to 0 to positive. So checking the gradient either side confirms that we have a minimum point at x equals 0. Now what about the second derivative? Well, at x equals negative 0.5, the second derivative is 3. X equals positive 0.5, the second derivative is also 3. So notice there is no change in the sign of d2y by dx squared either side of x equals 0. So this again shows us that we do not have a point of inflection. We have a minimum point. And this means we have to be careful. Just because your first derivative and your second derivative are equal to 0, this does not mean that you necessarily have a stationary point of inflection. It could, in some instances, and this is a good example, be something else. So if you're not entirely sure, the best way of checking is to make sure that you use the first derivative to check either side of your suspect point, because the first derivative will uncover very easily and very carefully what you have. So we're now going to take another worked example, and we're going to look at 4 elements of this function, y equals x to the power 4 minus 2x cubed. So the first thing that we're going to do is find any roots. So we know that at a root, y is equal to 0. We're looking at points where the curve crosses the x-axis. So x to the power 4 minus 2x cubed equals 0. Do not move one part over to the other side and then divide through by x cubed. Factorise. X cubed bracket x minus 2 equals 0. And this gives us a repeated root at x equals 0 and another root at x equals 2. And of course the y coordinates are 0 and of course 0. So we have 2 roots. So our next task is to find and then classify any stationary points. So for this I need my first derivative, dy by dx, and this is equal to 4x cubed minus 6x squared. Now we know at any stationary points, dy by dx is equal to 0, regardless of what type of stationary point we have. So 4x cubed minus 6x squared must equal 0. I can divide through by 2 to give me 2x cubed minus 3x squared equals 0, but I will not divide through by x squared, as again this results in loss of a solution, loss of part of the solution. Factorise instead, so we get this, and we then straight away see that we have a repeated root at x equals 0, and then x equals 3 over 2, a single value there. Now I'm going to aim to classify these by using the second derivative first of all. It's a valid method, we just have to be careful if the second derivative works out to be 0. So this gives me, for the second derivative, 12x squared minus 12x. And let's investigate both of these points. So at x equals 0, the second derivative is equal to 0. Now, this means I need to investigate further. It could be a stationary point of inflection. It may be something else. Remember the warning example we've just done. We don't know for certain until we check dy by dx. Now, at x equals 3 over 2, the second derivative is equal to 9, which is greater than 0, so this is absolutely fine. This is a minimum point. So this one is a minimum point, and we can work out its y coordinate in a minute. So let's now investigate this point where x equals 0. We know that the first derivative is equal to 0. Let's investigate what happens either side. So what happens at x equals negative 0.5 and what happens at 0.5 if I substitute into dy by dx? Well, I find out that at x equals negative 0.5, the first derivative is negative 2, and x equals 0.5, the first derivative is negative 1. So this means we go negative, 0, negative, and I always need to sketch out what that means. So that means the gradient goes from negative to 0 to negative. So what do we have? We have a stationary point of inflection. And we needed that confirmation from the first derivative. So I now know that at the point x equals 0, we know that y is equal to 0, and we have a stationary point of inflection. We also have the point x equals 3 over 2, and what I want to do, just to finish off, is to make sure I work out the y-coordinate at this point as well, which I can do by substituting back into the original function, and y is equal to negative 27 over 16, and this one we worked out was a minimum point earlier on. So, part 3, find any non-stationary points of inflection. So we need d2y by dx squared, which we had earlier on. It was 12x squared minus 12x. And let's see what happens if d2y by dx squared is set equal to 0. Gives us a very simple quadratic equation. Divide by 12 and then factorise. Now, we know x equals 0. We've just dealt with that. That is our stationary point of inflection. But you can also see that we get a value of x equals 1 from this equation. So we need to investigate this further. So let's check either side of x equals 1 as to what the second derivative is. So x equals 1, the second derivative we know is 0, because we found it from solving d2y by dx squared equals 0. The other two values you need to sub into d2y by dx squared using your calculator, and you will find that at 0.5 the second derivative is equal to negative 3, so it's negative. And at x equals 1.5 the second derivative is equal to 9, so it is indeed positive. So we can see that d2y by dx squared changes sign either side of x equals 1. So we have a non-stationary point of inflection at x equals 1. Now we could also have solved the inequalities created from d2y by dx squared being set greater than 0 or less than 0 to obtain this result as well. So the last thing that we're going to do is explore the shape of this curve. So can you see we've got the graph of y equals x to the 4 minus 2x cubed. And let's run through the different things that we identified. So remember that there were in part 1 roots, and the roots were at 0, 0 and 2, 0. So can you see those? There's a root there, and there's the other root over there. Now, in the second part of the question, we identified stationary points. And where did we identify stationary points? We identified stationary points at 0, 0, which was, of course, a stationary point of inflection. And you can see that there. That point, which happens to be a root, is also a stationary point of inflection. And then the other point, 3 over 2, negative 27 over 16, is a simple minimum point. And you can see it over there. Now, in part 3, we identified a non-stationary point of inflection. and our non-stationary point of inflection occurred when x was equal to 1. We didn't work out the y coordinate at the time, but we can very simply substitute into this equation to find out that when x is equal to 1, y is equal to -1. So this point here is our non-stationary point of inflection. Now, notice the curve in this section here is concave upwards. If you want to, you could draw in a dotted line to see the curve fall underneath the line, and the curve in this section here is concave downwards. You can see that there. Now, after x equals 0, or before x equals 0, there's then another shift. Have a look at this section of the curve. Can you see that if we do that, it becomes very clear that this section of the curve is also concave upwards. And that's because, of course, there is a point of inflection at x equals 0 as well. So that results in the curve transitioning from concave downwards to concave upwards in this section over here. So you can hopefully see the 2 points of inflection and how they break up the curve into these different sections of concavity. So we're going to finish this off with a very quick summary of some of the key points. Now, you've already learnt that a function is described as increasing if dy by dx is greater than 0 at a particular point on that curve. Conversely, a function is decreasing if dy by dx is less than 0 for a point or for sets of points on that curve. We then know that for a stationary point, dy by dx is equal to 0. Now, under the umbrella of stationary points, we then have the 2 possibilities of a minimum point or a maximum point. And it's important to understand that these are called turning points. So turning points include simply minima and maxima. Now, how do we know if we've got either of these? Well, we can use the first derivative. Remember, for a minimum point, the first derivative changes from negative to 0 to positive. And for a maximum point, the first derivative changes from positive to 0 at the maximum point to negative again. So we can identify turning points using the first derivative. Now remember, we can also use d2y by dx squared to identify a minima or a maxima. We know for a minimum point, d2y by dx squared will be greater than 0, and for a maximum point, d2y by dx squared will be less than 0. So if dy by dx equals 0, there are 3 possibilities. 1, a minimum point. 2, a maximum point. And 3, of course, there is the option of a stationary point of inflection. Now, we can identify these using dy by dx because we'll either have a positive gradient, a 0 gradient, and a positive gradient, or a negative gradient, a 0 gradient, and another negative gradient either side. Or we can use the fact that d2y by dx squared is equal to 0, but be careful because this can be misleading, as in the warning example we did earlier on, so it's actually best to double check by using the first derivative, which will always give us the answer that we are in need of. So always think back to that example of y equals x to the power 4 plus 2, where we had a point at which dy by dx equals 0 and d2y by dx squared was equal to 0, but it was not a stationary point of inflection. It was in fact a minimum point, and the only way we knew for sure was by using the first derivative to verify this. Now, if we're looking for a point of inflection in general, d2y by dx squared equals 0, but if it's a non-stationary point of inflection, dy by dx cannot be equal to 0. Also, at a true point of inflection, d2y by dx squared will change signs either side of the point. And that leads us on to the last 2 points here. When a curve is concave upwards, we know that d2y by dx squared is greater than 0, and when a curve is concave downwards, we know that d2y by dx squared is less than 0. And we know that curves will transition from concave upwards to concave downwards if there are any points of inflection, stationary or non-stationary.